Yeah, so if you measure it this way, we find a value of 67, or 68, something like that. If you go and measure it directly by observing how fast galaxies are moving away from us, you find a value of 74, 75. But both are precise. It's 67 plus or minus 0.5, and 75 plus or minus 0.5. So they are they don't work with each other very well. So we have a problem.
And what is being made to answer that question about the
Good question. So some people say the people who measure the supernova rates are wrong. They're making a mistake somewhere. Some people say there's a measurement error here. The other thing you could do is to say, well, when I get this value of h here, it's because I have assumed this model. Right? This is not a direct measurement. This is me saying, I have a model and I fit the three parameters to get the value of h. But maybe my model is wrong. Maybe there's an extra particle. Right? Maybe there is extra changes in the laws of gravity. Maybe there's something I need to add to my model that will make that value of h change. But also we don't really know all of the details. So this is a big question. We don't really know what to do. Good. Okay. So this picture of the universe from this cosmic microwave background, is the baby picture of the universe. We know what the universe was like 380,000 years after the Big Bang. Now, the idea of the cosmological model will tell us how these fluctuations, these tiny variations, will grow in time. They become bigger and bigger, they become denser and denser in some region, emptier and emptier in other regions. And then these will form clusters of galaxies, they will form stars, they will form planets, they will form us. How do we test all of this? Right? This is a prediction, so we say this is our model, but we want to test all of this. So the main question is how we go from top left. This is now a newer picture of the cosmic microwave background, so look at the right. And I've already told you this is what I do. Well, what I try to do is how we test all of these theories, and typically we put them in a really big supercomputer, or as big computer as you can get, and you try to get a computer to answer the questions for you. Right? And the rest of today, we're talking about why we do these kind of calculations. Okay. Shall we have any questions at this point? Yes.
I have a question.
Yeah.
The last is where is the system reference in that picture on the top? Where are us?
So,
Where?
this
the
one.
other one in the top.
Ah, yes. Okay. So yes. So we are in the middle, and so this is a strange way of plotting things. So what people do? So we are in the middle. We're measuring the whole sky. So we're measuring the whole sphere, and then you try. It's a bit like when you make a map of the world, right? So the whole world is a sphere, but how do you make a map that fits in a rectangle or in some shape that doesn't do too much deformation? And so people use this kind of shape to represent. It's like taking a sphere and completely open it up and like that. So it's looking, we are in the middle of it. It's like if you try to take an orange or a fruit and you try to peel it in a way that gives you a sensible map.
Go back to the question of how we know if the universe was created yesterday. How we know the universe has 30,800
yes.
years.
So if we can measure the temperature of the universe at that time, then we can measure the temperature of the universe now. Right? We can just go out and measure it. Then we can know how, and we know the law of physics, we know how the temperature changes with time, then we can make an estimate for that. And we can also do other things, like if we know the rate with how much the universe is expanding now, so this measure of h, I can ask the question, if I extrapolate this back in time, when does this become close to zero? So there are different ways you can do this estimate, and they're all around this number.
Why do we use to assume a parameter curvature is zero if it is any fluctuation.
Yes, so that's right. So when you have that model here, you can try to fit more complicated models. One of them would be that the curvature is non-zero. But actually, if you try to, so you can do this exercise. So here I'm only showing the 6 parameters that are. But if you try to play with the curvature, I forget exactly how it changes, but it just doesn't work. So the data doesn't model the universe with any non-significant curvature. You can also play other things. You can say, are there any extra dimensions, or are there any other particles or something? There are many things you can't do because the data is actually very constrained. There are not many things you can do to get the green curve to go through the data points. Good. People in the coffee? No? Yes? Coffee time.
Muchachos, los de Galaxias, ojo, todos los días va a rotar una lista con asistencia. Si usted no la firma, no vino. Ya sabe qué pasa. Es este moscas que por ahí las dejan, por eso está primero la dejan quieta. Si no firma, no vino. Entonces estén pendientes ustedes. ¿Listo? Porque estamos reventados. Ya la lista. Ya me la pero solamente me
Pero me la mandaron desde la
¿Qué más, Bruja? ¿Cómo va?
Ay, qué chido, ay, me estoy quedando medio.
O sea, prefieres la sola.
Nunca la tomo, pero yo también los tomo es con mi lectura, sabor a la es una parte de estofar. Ya, el arroz con leche salida o el arroz con leche. Sale el sol, bueno, y con queso. Pero en general, arroz con leche es fácil.
No, es que esta lista de hace un momentito de afán. Tienen que vaya.
No, bueno, los 14 Sigue la escala ahí de la casa.
One minute, please.
Somewhere in your presentation, you showed the cosmic microwave packages. And one was like and the other one was like two cones.
That wasn't the cosmic microwave. That is the. I'm gonna quote this one now. This is the one was in the bottom right. This is not the cosmic microwave. This is bits of the universe now, where every gluon is a galaxy. It's just a gap of the present day.
Why
is it the code? It's a code because wherever the telescope was, it could only see this part.
all right.
So in this case, we are the center of that. So we are there, and we can see there's everybody that can see galaxies, but that makes you map of the universe. And then you activate that. That distribution of dots usually given statistical. You need a different telescope in a different place. So when you are somewhere on a mountain, you have to see part of the sky. So that's why you go to space. You can see everywhere. Apart from there are some places that don't look at the sun. Sorry. Not the first sky, but you want to avoid it. You are inside the way. So we are where on the side. So seeing through the waves, there will be some things in the sky and we still don't have the map. Well, it doesn't matter if you see it. Are we ready? Good. Okay, so we stop at the story of where we measure the start, we measure the cosmic microwave background, cosmic formation. Now we can observe the present day. And now the question is, do we have a theory that goes from the start to now? And does it all work? Is it all self-consistent or are we missing pieces, right? So we want to understand a bit of this, what we call the large-scale structure, so sort of this filamentary structure I showed in the first movie. How does it evolve? Can we complete this? Right? So that's the goal for the second part of this movie. Okay, so there'll be a bit more equations. Not going to solve anything, but just showing you some of the key ideas. Okay, so the first thing we assumed was that the universe was the same. When I said at the start, we assume the universe doesn't have any special place. In other more technical terms, it means it's isotropic and homogeneous. And then if you do general relativity, first of all, good luck. And then second is that if you do general relativity, there's only one solution that is able to represent this, that tells you the shape of how the equation behaves. So that should tell you how the metric, which is sort of the key component of general relativity, we're not going to go into the detail, but there's only one possible solution. It has an equation like that, right? And this is sort of a solution that's been derived by these four people. And then the key term here is that there's only one free thing, is this A, which is the scale factor, which is sort of the size of the bit of the universe. And it has a value of 1 today and 0 when the universe was infinitely small. So that's the only free, and it can only be a function of time because we assume that everything is homogeneous. We have one free function that we have to solve. And then, well, we apply Einstein's equation. So because they are probably correct, they happen to be also on the wall at Leiden University. Because they like to put equations on walls. And then here, if you can't read the wall, this is what the equation would look like. Again, I don't want to go into the detail, but once you have decided what this G has to be, you can solve for things, and then the equation of general relativity, they are in spirits. Of course, they're like, so you can see like a four-dimensional tensor equation, very complex, but essentially they tell you what is the content of the universe on one side, and how the universe changes on the other side. It relates both of them. And so once we have decided what the content of the universe is, what the shape of this G has to be, then we can sort of try to solve for this parameter A. We can do all the mathematics, and then we end up, what Friedman did, is that we end up with only two equations, and then describe how the whole universe evolves. Right? And you asked about curvature before, so if you leave the curvature in, you still have a K here that's but usually K equals 0 is a much better, works much better in our case. And so this differential equation tells us how A evolves as a function of the density, maybe of lambda, and maybe also the pressure of the filter. And so this essentially tells us how the whole universe can evolve depending on its content. And now, so that's a huge simplification compared to the full actual equations. And that's actually a tractable problem. It can be solved, and we can check how A evolves. Right, and so you have these different terms, the curvature term, exposure constant, and a few other things, and then a bunch of constants, which of course that's not a problem at all. People usually simplify the notation, and we have seen this omega before, but essentially what we do is that we divide everything by the mean density of the universe, the critical density of the universe, and then we can write the whole equation in a much simpler way, where we have h's and then these different omegas that tell us what is the fraction of the universe content that is made of a specific species. So omega matter is the amount of the fraction of the total universe energy density, which is made of matter. Omega lambda, how much of this is made of lambda, and so on. And a good number to keep in mind is that the average, so the critical density of the universe is this bunch of constants here, which turns out to be about 140 solar masses per kiloparsec cube, which probably doesn't mean anything. But it's a good number to keep in mind that this corresponds to about 6 atoms per cubic meter. That's the average critical density. Now this is an extremely good vacuum, right? If you go to the best places on Earth in experiments where people try to make vacuum where it's completely empty, there are many orders of magnitude away from this. So this is really empty compared to what we humans can. Please.
Why is omega 0?
Probably because I copied this one from Wikipedia. No, the 0 here is, okay, because you can have things where...
The whole quarter is relation, matter,
No, sorry, the 0 here means present day, so it's at present day the omega radiation, present day the matter,
yes.
and so on.
That H is Hubble parameter, right?
That is the Hubble parameter now, and this is how it's
The
before.
density.
Yes,
It means that course density changes in time.
correct.
The whole universe.
Yes, because the whole universe becomes smaller, and so that the critical density becomes higher.
Then the probability C0 should change depending on which H0 you choose, right?
Well, this is 1 at 0.
No, the density of the whole universe today.
Yes, it changes with time. Because the universe is growing. Like if the same amount of material, but the universe is getting bigger.
I mean, you should choose which H0 you use.
Here.
We have.
Oh, you mean because of difference in measurement? Yes. Yeah. So that has consequences everywhere, right?
And which one we choose?
I mean, the difference is only a few percent between the two. So, it's going to be 6 or 6.06 atoms. Just to give you an idea. Okay, and so relating this to the chart so before, these are the different components, right? So we have dark matter is this one, radiation is this. Radiation is very small, it's only 10 to minus 3. You can just usually ignore it completely unless you're doing very high very early universe physics. Curvature is almost 0, and then the lambda, which is a dominant term. Okay, so I showed you this graph before. So this is now. So this is, if we go back in time, what are the dominant components? At the present day, it's dark energy, which is dominant in terms of quantity. If I go back in time, it will be omega matter. And if I go even further back, it's going to be omega radiation that dominates. Because if you look at the equation, right, they change. This one doesn't have a power of A to the minus 3 and A to the minus 4. So at different epochs of the universe, different components are the dominant energy content. Okay, so this is theory, but that we can actually measure, at least in part. And people have done that. So this is now from the 1998 to 1999 paper by the Salper-Mutter. And so what they did is that they measure as a function of redshift. So redshift is this A, that's 1 over A minus 1. So this is, you can measure this easily, so how things are moving fast and moving away from us. And then this thing here, you can think of it as some sort of function of H, which we can go into the detail if someone's interested. And then, there's these data points from different supernova measurements. And then you have different models, different lines going through. So again, you can decide whether that's a good fit or a bad fit. But you have different models here with different values of omega matter, omega lambda, and omega k, which are plotted to. And then based on that, you can decide which is the universe that fits the data the best. In this paper, they argued that the best fit is a flat universe with omega lambda is 0.7 and omega matter about 0.3. And then that's why they measure the, so you can, this is supernova 1A measurement. And for that, they got a Nobel Prize in 2011 for the quality of this measurement, right? So, but you can see it's a very difficult measurement. You have all of these data points, and then deciding which line is the best here is a tricky exercise.
I'm sorry, that some function of H, is that the last?
Yeah, it's the last stage. And so these guys, this gentleman here, got the Nobel Prize for their discovery or for the measurement, and then you can't really read it here, but Perlmutter is also Berkeley. So if you win a Nobel Prize at Berkeley, you get, as a bonus, your special permission parking spot that he seems much more happy to have here than he was on the previous mission. Right? So now they have 2 parking spots reserved for cosmology people. I don't know if they have many more parking lots that they can dedicate to this kind of things. Right? Questions on this part? Yes?
It's like the question about the first principles, about the isotropic and
Yep.
sequence. Because you mentioned that the cosmic matter background has different regions of colder and
Yep.
hotter. Why do we say that the universe is homogeneous and isotropic, but we have different
Yep.
temperatures?
Okay, so it has very small, so the assumption is that it's almost perfectly homogeneous. Like the average is homogeneous, but there are small fluctuations on top of it. But the fluctuation don't depend specifically on position. But it's a choice. But if you make a different choice and you say, I don't believe this is true, we have to go back to the start and make a different derivation of all of the equations. Because now this A that only depends on time also has to depend on space, because different regions of the universe might grow at different speeds, for instance. Okay? If you look at the data, if you look at trying to measure the distribution of galaxies or difference of matter nowadays, it looks like it's very homogeneous. And there's no data at the moment that has convincingly shown that we have a problem. But that's an assumption we have made. Isotropy as well, but it's the same in every direction. It's a choice. It's a very, very difficult measurement to make to see whether it's true or not. But it's a bit of a philosophical choice as well. You say, we are not in a special place, so we like that choice. And as a consequence, you have to make that physics, this definition of homogeneous and isotropy. Okay, beautiful. Yes?
The measurement of the redshift with the new telescopes,
Yeah.
can it affect the behavior of this graph?
Okay, so I showed you the original one from 1998. Now we have thousands of supernova. They have much better measurements, and so now it's very, very clear from the data that this. So yes, the better measurements. Yeah. And also, this is based on supernova 1A. These are special stars that explode in a very specific way. Our understanding of how these stars evolve and explode also helps understanding and making the error bar smaller, because we start understanding the physics better and better. Okay, so now so far we've looked at how the whole universe grows. But as I was just mentioned, there are different blobs, right? And these different blobs are supposed to be forming different dense regions or empty regions. How do we get there? Okay, it's going to be a bit of dirty work, but what we're going to do is that we're going to assume, and that's not a bad assumption, is that what we're looking at is mostly gas, especially at the early stage. It's like hot gas. So what we're going to use is use the equation of fluid dynamics, right? So there are three equations. First one telling us that mass is conserved. Second one telling us momentum is conserved. And the last one is just telling us how gravity works. And here we can just use Newton's equation. So these are the basic equations that describe how the fluid under gravity will behave. So we have a few things like density, we have the velocity vector, there's a pressure here, that's the potential, and so on. In principle, you should be also doing this in a universe that expands, so there should be some A and some other things that become a bit more messy. So that we can see that just in the description here. So we have the velocity field and pressure and so on. And so now we want to talk about the fluctuations, right? So how we evolve. So how do we do? So this is the thing which, you know, when you do physics, there are two things that you have to know in physics, and the rest is just details. The first one is how to solve the harmonic oscillator. Every problem, because this is the only differential equation that we know how to solve. So anytime you have a problem you don't know what to do, you check whether it looks like a harmonic oscillator, and then you have it. And if you can't do the harmonic oscillator, you do the second thing, which is called perturbation theory, where you assume something is constant and has tiny fluctuations around it, and hopefully a harmonic oscillator will appear. So we're going to do the same trick here, and it's actually working very well. I told you before that these fluctuations are order 10 to minus 5 compared to the mean temperature. So 1 plus or minus 10 to minus 5 is a very small number, so it's kind of pretty justified to say we're going to use perturbation theory. So we're going to define the density to be some mean density times 1 plus delta. And then we're going to see how this delta evolves. Just to simplify things, what we do, cosmology usually is what we call co-moving positions. So we're going to take all of the equations where everything is expanding, and I'm going to divide everything by the expansion rate. So I don't have to worry about things growing. I'm defining co-moving positions as being the real position divided by this A. Right? So now I am expanding with the universe. So my everything is expanding with the universe, so I don't have to take this into account. That simplifies a lot of things. All you have to be careful with is that the velocity, if you take this, this R equal x times A, there's a bit of chain rule, you have to be careful. Then you get two terms of the velocity. You have one which is A dot R, which is just actually the velocity from the universe expanding. And then you have the velocity that you are moving on top of the evolution, the expansion itself, which we call the peculiar velocity. So this is the velocity of the fluid with respect to the background. It could also be the velocity of a galaxy with respect to the background, or the velocity of anything with respect to the background. So you can think of this as being sort of the Hubble expansion, 70 kilometers or something, and then this would be whatever is moving on top of this, like average expansion. I'll go back to my equations. I don't want to go into we don't want to go too much details, but I replace all of my positions by co-moving position, my velocities by peculiar plus Hubble flow, and I replace my densities by these 1 plus delta terms, and I'm left with this sort of complex system of equations. Now, what we're going to do, because otherwise it's going to be complicated, is that we're going to assume we are looking at cold dark matter. So I told you we're doing the fluid, but it's going to be a good approximation anyway. And then because it's a dark matter particle, we're going to assume it doesn't have any pressure or anything, and so it doesn't have any sound speed, and so that's going to be 0. Okay, we simplified one term, but that was the dirty one, so that is good. Now we're left with the rest of the equations. The thing also works if you do things, it just gets more complicated if you don't do CDM. And so then if we remove everything, right now we're doing perturbation, remember it's perturbation theory business, what we want to do is remove everything which is high order, so everything, anytime we have a delta square appear, or something that has sort of high power of delta or something, we want to eliminate that because we want to only look at the regime where delta is very small. So we're left with this equation here. And now we have an equation for delta. It's still a very dirty differential equation, right? We have a delta dot, right? here we have a spatial derivative of delta that also depends on this A complicated thing. And that's a very complicated question, so please.
Can you go to the previous slide?
Yes.
That term that you just like eliminated,
Yeah.
Contains the speed of the fluid that we assume is the universe, right?
The main content of the universe.
The main content,
Yes.
right?
The main content of the universe.
The main content.
Yes. So that's called dark matter here. The whole thing also works if we do gas, and then in which case that would be something like the temperature. The equations become even more complicated, and we don't, for the argument I'm trying to go through, we don't have to go look at that. But the whole system works if you do the whole thing in detail as well. It just gets even more complex. So we are left with this. Well, that's not a fun one. Okay, so I told you there are two tricks when you're a physicist. You know the one third trick how to solve something when you're a physicist. You don't know what to do. Well, I already eliminated terms by arguments before, but that's not a good trick here anymore. The one trick when you don't know what to do is you try to solve everything in Fourier space, because somehow magic usually happens in Fourier space, and then some of the terms may still simplify. Not always a good trick. When you don't know what to do, you go to Fourier space, and maybe things will work better. So that's what we're going to do. We're going to define delta at a given position to be some sort of sum of delta k waves, right? Which is good, right? So I'm not saying Fourier space is just magic. It's like very good at eliminating all kinds of derivatives and turning everything into algebraic equations. Instead, there's a reason behind this works. It doesn't always work, but when you don't know what to do, it's a good trick. And so if we simplify our equations now, we are left with, so we can eliminate some of the derivatives, and we're left now with something which now has only derivative in time of this delta. And we eliminate the space, which is good because that's much easier to solve. And that's a harmonic oscillator, right? Or a damped harmonic oscillator. So we're in happy land, we'll be able to solve this. So a damped harmonic oscillator in Fourier space. Once we have the solution, we can go back to real space, but that's it. Matter. We go, we live, we're not happy. So what we have here is that we have the usual thing. So we have the decayability, then we have some sort of term in it, but we also have a damping here. Okay, so a lot of equations for this presentation. But you can think of this term here as being pressure versus gravity. So you have this term which I eliminated before, but I'll put it back in for in a minute. So we have something like temperature minus some sort of gravity. So there's a battle between how much temperature there is and how much gravity there is. Right? And so you can see where this is going. If something is very cold, then gravity will win. If something is very hot, you can resist against gravity. Good. So let's analyze a bit what we can do with this equation. So if I make my sound speed, so k is this wavelength, right? It's not the curvature anymore, so the wavelength of the Fourier mode. So if I make this term here very big, so there are two ways I can make this very big. One is I can make the sound speed very big, so I make my gas or my something we're looking at very hot, or I can make a very small, so that would apply the reverse. Then this whole thing is positive, and then harmonic oscillator happy land, we end up with some sort of sine waves. Okay? So now our delta is just moving as sine waves, so you essentially have sound waves propagating through the universe. So these fluctuations we saw in the CMB before, they just evolve slowly in time. And that's all there is. There's nothing more happening. If not, if I change that, if I make this term, then gravity wins, and we have a problem. Well, we don't have a problem for sure, but gravity wins, so that is good. First of all, we are forming structures. So these fluctuations are now going to grow. They're going to form denser and denser and denser regions. Right? There's no stopping of gravity. We're making something denser and denser, which means we're going to be forming dense regions, which we call halos. And then in there, we're going to probably form galaxies. Then we're going to form stars. And then that's where everything stops, because we can't form anything denser than that. We're going to form, and we're going to form planets and everything, right? So we need this to actually happen. So we need to be in a regime. There need to be a region of space where this thing here is smaller than that. So there will always be, because it depends on A, tells you that at late times when A is large, then that will probably help. And then especially if I make thing small in terms of sound speed, then that will also help, because then that whole thing is zero, so it's always going to be smaller than that. Good, we're forming structures. Problem is that we started by saying delta is small. And now I'm making delta grow exponentially big. Right? So we have a problem here, because we start with an equation saying that in perturbation theory, and we can't perturb anymore because this is way too big. But we eliminated all of them, which were large, which is small. And what is the main problem here is that I said before, if we're doing cold dark matter, then there is no pressure. That is zero. And so all scales, right, not just specific Ks, all of the Ks, all of the size of all of the fluctuations are going to collapse. Gravity makes them win, right? And so we form structures of all scales. So there will be small structures, there will be large structures, there will be any kind of things, small structures on top of big structures and so on. Great. But we can't use our formula anymore, so we can't stop using perturbation theory. Good. What do we do next? Well, that's where either you are clever, and you go and you say, well, I did perturbation theory, maybe I can do second order perturbation theory or third order perturbation theory. And you can start adding more and more terms to my equations. And then, instead of just evolving delta for a tiny bit before it becomes too nonlinear, I can do a bit longer, I can do a bit longer, and I can see how the universe moves. But if you think about the level of fluctuation, so the start of the universe, we're at order 10 to minus 5. Okay. But we want to do the whole universe. I mentioned before, the average density of the universe was, in terms of atoms per cubic meter, 6. What is the average density in this room? Or in us? Or the water?
More than 6.
Sure, yes, that is not wrong. It's not a very useful answer, but it's not wrong. But so what the average, so the mass of, so take in water, we're talking about 10 to the 27 normal temperature, right? 10 to the 27 atoms per cubic meter or centimeter. But anyway, more than 20 was a magnitude more. Even if you ask what is the average density in the inside the Milky Way, just inside the gas disk, it's also orders of magnitude large. So we are in a problem here is that pretty much anything we want to do about galaxies or dense regions, they're way beyond this average density of the universe. Okay. So then my solution, because I don't want to do perturbation theory, is that we have to then start looking at simulations, because then computers, instead of solving the approximate solution, we can actually try to approximate the real solution by using computers to do all of the math for us rather than we doing it. There is just an example of these. This is from a recent simulation. Well, I don't see very much. It's too dark. But what you see is an average speed of the universe. And again, I've taken the expansion out. So we're looking at this comoving frame, right? And what we see is that, or what we can't see, but you should be able to see, you can come and look at it later if you want, is that what started in a very, very uniform setting is now forming this. Oh, great, yes, it's better. Let me play it again. Okay, so we start with a very uniform region, and then rapidly you form this. So the color here is showing the density, right? And you start forming these fluctuations. You form what we call filaments, and then at the center of these filaments there will be what we call the halos, and that's where the galaxies. And so we form this whole network of filaments. So this is called the cosmic web or the large-scale structure. Yes.
Which equations are solved by the
Here, gravity. That's it. Right, so I start with a bunch of. We'll talk a bit more tomorrow about how we go about doing this, but essentially what we do is that we start with a pretty much uniform density field, and then we solve the equation of gravity step by step in the computer, which is not doable by hand. It's too much work, but that's what we solve.
But those are the ones that we just.
No, before we did an approximation, we said because I can't solve the full set, it's too complicated. I'm gonna use the perturbation theory to solve the reduced version, which is only valid for delta is 4. Here we solve the full set.
Okay.
We don't do the approximation. And someone earlier was asking me, I showed this picture in the bottom right showing this sort of wedge in blue, with like it was in red, showing all of these galaxies in these dots. And so this is what you see here as well. In the simulation, what emerges is this large scale structure. You see this alignment of structures that is a prediction. Right? So this is essentially telling you these fluctuations you see at the start, they will grow and then will collapse in different directions and then will form these filaments or these halos. And that depends on different things. It will depend on the initial states, it will depend on how much matter there is, how much lambda there is, how much everything. It depends also on the law of gravity. So if I make gravity stronger or weaker, the shape of this fluctuation will be different. And if I make gravity weaker on large scales or on small scale or whatever, I can change the pattern that is created. So if I want to test my theory of the universe, I can go and measure these and then compare to simulations where I have my different laws of gravity implemented, and I can tell which of these models is wrong and which one is right, or all wrong.
How do we experimentally check this web-like structure?
Okay, so one way you can do it is you can just go measure the position of galaxies. So what you can do, you can measure two angles in the sky, that's very easy. And then if you have a redshift, you have a position. So now you have two angles in the distance, so you can make a 3D map. Right, so you can make a 3D map of all of the galaxies. If you now know a lot more or a bit more about the properties of galaxies, you can make good choices about which galaxy to select to make it more robust and precise. You can make a measurement like that. The other thing you can do is you can do statistical thing. You don't want just to make a map, but you want to measure like a correlation function or a distribution function or a power spectrum. Like do the Fourier transform of this, Fourier transform of the map, and you can compare it. Okay, so to go beyond simulations, and that we're going to be talking about this more tomorrow about what is the kind of equations and how do we actually solve some of these, and how do we get a computer to learn about this. Then we can come back to theory on Thursday. So just a couple of examples of simulations because I thought some of them are quite fun. So this is, as far as I know, this is the oldest simulation. Oh, okay, so I don't know if you have heard of. So what is the first simulation of gravity? Do you know that? So it's quite a fun one. So Holmberg, I think was his name. And so what we realize, so if you're doing Newton gravity, so the force of gravity goes as 1 over r squared. That's the distance, gmn over r squared. And now what he thought is like, well, look, if I have a light bulb, the light I get also goes as 1 over r squared. Like the amount of light I get as a function of distance also goes as 1 over r squared, right? So what he thought about doing is that if we're going to put a bunch of light bulbs that will all be mapped, such that you can think of the light bulb as a given light to be a mass of 1. Then if you go far away from this group of lights, you can measure what is the intensity of the light there, right? And that would be like the intensity of the gravity you would have received. And you can measure this. You can take a lot of students, and they all go and measure the amount of light they receive at every other point in the system. So they did this with like 20 or 30 light bulbs. And then you measure for each of these, and then you say, okay, this is the amount of gravity that would have happened here. And now I can move my light bulb by a tiny amount because this is how it would have moved over if I had a very short delta t. So it's not really a simulation in a computer, but it's almost like a simulation because you do an approximation by having a very simple process. Right? So that's like from the 1940s. So this one is one of the first, I think it's the first simulation for which we have a movie. And so this is nothing. This is Lindblad. If you've done any galaxy theory, Lindblad has had some theory about how you form spiral arms. And then he had some theory of pen and paper, and then he went and developed some computer simulation to test that. So what is showing here? So this is from 1960, and the reason I have a copy of this is this guy, Per Lindblad, he was going to a conference in the US, so he's from Sweden, and on the way he was stopping in line, and he wanted to prepare a movie to show people, right? But at the time, when we were giving a conference, of course, even having a projector was very unusual, especially if you wanted to have a movie projected. So they actually had to go to the cinema in town and asked the cinema whether they could borrow the projector to show this like physics experiment to people. Right? So that was so there you can read about it. There's the whole history of the whole thing where they have to organize for this. Anyway, so what I like about it was always quite fun in the style. So you have a title. It's like what is missing here? I don't have seen this old movies where you have people playing the piano to make the sound. It's very much the stuff. So it's showing you here that this is a galaxy which is perfectly symmetric. Although he's making a small, he showed you with arrows where he's just making a slightly more dense region. And then it's just solving the equations and showing you that as you evolve it, this sort of deformation happens. Then you put a tiny clock at the top here to show you how the time evolves. So you can see that my movie didn't have a clock. I should probably have a clock. I think that looks pretty good. Show you how things, and then how these deformations go. You go in time, and as we do a bit, we'll see how some of this will break up. And it forms some spirals. Right? So this is very, very simple. This you can do today in 2 seconds on the computer. Right? This is but it was quite fun to demonstrate. So that was the first demonstration, and showing also how computer simulation. So although we had done it by hand also analytically, so you could say, well, why do you do a simulation in this case? But still, demonstrating that you can learn something from simulation to test your theory. Right? And so here was just evolving 116 stars or something, and then to calculate all of the forces was taking 7.5 minutes. Right? So he has 116 stars. They all have to calculate the force with every other one. And that was taking about 7.5 minutes. And then you would do this many steps. And every so many steps, I don't even know how you had a printer or anything, how you made a movie. But every so often, you just print out all of the dots to make a movie of the galaxy, and then put them together in a way that I don't know. And then you find a local projector, and you can tell all of your physicist friends that you solved galaxy formation, or how you solved spiral formation. So that was pretty cool, but people also realized that, so you can do this, but the kind of other things that people are looking at, especially now in the 70s, they're trying to do cosmology. Right? As said before, we can't do this equation, this perturbation theory doesn't work. So these three Russian scientists here made a simulation of a region of space collapsing under the equation of gravity. And I showed you in my movie before, you have these filaments. That's also what they had already. They found that this worked pretty well. What is quite interesting here is that, so here when they were trying to represent the density by putting dots, wherever, but at some regions, if you can probably look at it later, their printer wasn't precise enough to put a lot of dots next to each other. So they actually put numbers to tell you how many dots are. So it feels like this is 3, here there should be 5 dots here, right? And so on, because they didn't have enough, the printer itself doesn't have enough precision to put dots so close to each other. But you can still see, filaments happening, a halo here properly forming, and then some void region in between, which is also what we still have in movies today. So still, it was already giving us some cool results. Here's another one. Now in this paper, 79, Sven Arset is still working on this. He's still writing some code, this n-body code, which is quite famous. Every time he has an update, he emails people with the changes of the code. So it's very old school style of code updates. GitHub, not for it. So it just sends you a patch. So these are the changes, apply that to my new version of the code. But you can see early universe, very uniform, and then halos forming as well. Here's another one. So this is from, again, group of Russian clipping. So now in this simulation, now they have 32,000 particles. So this, all of the Lindblad had 116, this is 32,000. And so you asked before, how do you know dark matter is cold? Well, one of the reasons is because it doesn't work if you make it hot. And I'll show you in a minute another picture. But so what these guys are doing is that at that time in the early 80s, there was a measurement by Lyubimov of the mass of the neutron particle. That result was wrong, but it got a lot of people excited. And everybody was thinking, oh, if we measure the neutrino mass, surely that can be the dark matter particle. And then people started looking at theory, whether you can use the dark matter particle as the core, as the dark matter, using the neutrino as the dark matter. and then with a hot dark matter, because it's a very fast particle, in the experiment before, they couldn't cancel the sound speed, because like, it has very high sound speed. But it didn't work, and I'll show you why in a second, but they did simulations like that. And here is an example of why it didn't work. And so this is a very famous paper from the early 80s from White, Frank, and Davis. And what they did here is that they simulated different scenarios. Right? So this is what we still do today. So they simulated different versions of the universe. You have two versions here with cold dark matter, slightly subtle differences which we don't understand, and three universes here, where the dark matter particle is not a cold dark matter, but is made of neutrinos, so it's hot dark matter. And in this here is a CFA survey. So this is the first survey that was with very high quality data where people measured the wilds, and then what I mentioned before, so you measure the angle and the distance to a row of galaxies, and you make a map. And here, you don't even need to do any statistics to realize that at least 3 of the universes here are wrong. So at least these 3 models, they don't look like the real universe. So if you do hot dark matter universes, they do not work. They don't look like the data. And so this is one of the key papers that demonstrated 2 things. One is you can do cosmology via simulations, which is always a big job. People have to realize we're not just doing physics now by pen and paper and blackboard derivation and everything. We can use computers to learn something. We can use computers to learn something about fundamental particles, and we can eliminate different models. Right? And this sort of established the cold dark matter model as probably working quite well. At least it's not ruled out as data, and since then, many more simulations have been done, and they still working this way. So there are some changes you can make, but you can make big breaks. And here we can do it by eye. Of course, nowadays, the data is more precise. Our models are less different from each other, so we can't do it by eye anymore. I'm doing some more statistics. Sort of things. So if you move 20 years forward, this is another famous one. It's like the Millennium Simulation. Maybe if you've done anything in cosmology or galaxy simulation, you've heard of it. It was on the cover page of Nature in 2005. And what you have here is exactly the same game. It's a very big simulation. The previous one had 32,000 particles or elements. This one has 10 to the 10, right? So 10 billion. And it's the same game. Of course, in the paper you don't know statistics, but you have simulation in the red part here, and again, at the same time, observers have done a lot more developments, and they have much better maps, much better precision in everything. But you can see the same idea that you have the 2 models. Sorry, so these two have the same model, just different regions for fun. They look at least visually quite comparable, on average, statistically, to what the data wants. Again, if you want to do precision, not just looking at maps, you do some calculations. I forgot what this one is. Oh, yeah, this is just flying through that simulation. So what you can see here is this: we are going through a region of space, and you can see how we pass by some of these halos, some of these filaments, and how this density field is arranged. Okay. It goes on for a very long time. And finally, the largest simulation so far that people have run is called the Euclid flagship simulation. I mentioned before there's this Euclid satellite. It's going to be really, really precise measurements. So you need also really, really precise theory. So you need a really big simulation that you can compare to it. And so this one has 8 trillion particles. So that's 800 times more than the previous one I showed. And that's actually was running one of the biggest computers in the world. And then essentially simulated everything you can see. It's just so big that it's simulating the whole universe we'll never be able to observe would be in that simulation. And so people that keep playing that game. And the thing is, even here, if I look on my computer on the big screen, you can't even see it's so big. It's essentially looking very uniform because it's such a large region of space. But people are still playing this game over a bigger and bigger simulation because there's still no more. Any questions? Comments? Criticism? Yes.
Simulations is consistent with the observation. But you can be sure about this simulation show the universe us or Much better. The universe that you simulate in the computer are other universe. It's not our universe, and
Yeah.
it's not a problem.
Okay, so the universe in the simulation, we know exactly what is the physics that goes into it. So we know exactly the laws of gravity, the exact matter content, and whether our universe is the same or not, that's the question. If we see that our universe looks very much like our simulation, I can go and ask the simulation what were the rules for that universe, and then I learn something. I can't prove it's the correct physics. I can tell you that it is consistent with that. Now, the other aspect, so that's one aspect. The other aspect is that this is a random region. So what we are doing is random fluctuation start and then let it evolve. If I go in the simulation and observe, I will never find the same object. I will not find the coma cluster. I will not find the Perseus cluster. I will not find anything that you can see in the night sky. Will not be in the simulation because I did a random region. It doesn't matter because a lot of the game here is about statistics. I want to see whether I have the same number of big halos, small halos, or things like that. But some people are interested in that question, so asking the question, can I generate a set of initial fluctuations that when I evolve them forward, will look like the coma cluster, with the Perseus cluster here, and Hydra here, and all of this. And that's a very, very difficult question. So it's not a difficult question fundamentally, but it's a difficult question to do in practice. And we can talk a bit more on Friday. I have some examples where we'll try to do this. Okay,